example M7.1, the gantry structure in the photo is used to test the response of an airplane during a crash. So, as shown, the airplane having a mass of 8 megagrams is hoisted back until theta is 60, and then the pullback cable AC is released when the plane is at rest. Okay, so determine the speed of the plane just before it crashes into the ground when theta is equal to 15. Also, what is the maximum tension developed in the supporting cable during the motion? Neglect the size of the plane and the effect of lift caused by the wings during motion. Okay, so let's try and understand how this problem works first. So we have a plane here. When you release it from rest, right? You release this from rest, it's gonna go about in a circular motion, right? In this circular motion right here, somewhat like that. Okay, so since it's going about a circular motion, that tells us that this is a curvilinear motion, right? Okay, so we know that there is the presence of a normal acceleration and tangential acceleration at okay, for this situation. Next, we also know, right, that the initial point is at A and the final point is at B. All right, but since it starts from rest, what do you think is the contributing factor to the speed of the plane before it until it reaches point B? It's the weight of the plane, right? So it's the weight of the plane, right? It's the weight of the plane going downwards. Okay, weight of the plane going downwards. Therefore, the gravitational potential energy has a lot to do with the speed, right, at which the plane hits the ground, okay, at point B. And therefore, we will be applying the principle, no, not the principle of work and energy, the conservation of energy equation, right? Because we see that the although there is tension here, the tension doesn't do much for the movement of the plane, right? So the only force that is doing work on the plane is the weight of the plane, right? Okay, so first we have initial and terminal points. So we have A and B, and then we have to draw out the free body diagram, all right, in order to account for all the forces on the plane. Okay, so here we have a free body diagram, and it follows a curvilinear. Since it follows curvilinear motion, then we have to use the NT axis. Okay, this 15 could be 60, it could be 15, it could be any value for theta. Okay, but in any case, it's the same principle, right? You should know how to draw out a free body diagram by this point in time. All right, so next we apply the conservation of energy. And since only the weight does work on the plane, only conservative forces do work in the system. All right, so applying the conservation of energy, we have the kinetic energy at A plus the potential energy at A should be equal to the kinetic energy at B plus the potential energy at B. Okay, so the potential energy at A is the weight times 20 cosine 60. And where is this 20 times cosine 60 from? Well, this your datum is located here. All right, so since your datum is located here, okay, let me just get out this okay, straight line. Okay, so this is supposed to be 20 as well. Okay, this whole thing is supposed to be 20. So 20 cosine 60 is the distance from here to here, the datum to the to the point of the plane, okay, or point A rather. Okay, so that is 20 times cosine 60, because we see that we form a right triangle, right? Okay, and this is the adjacent side, this is the hypotenuse, and therefore this adjacent side, let's call it x. X over the hypotenuse, okay, is just equal to cosine theta. All right, so therefore x is equal to h cosine theta, right? Okay, so I forgot to tell you that the datum was located here. Okay, so you can situate the datum wherever you want, for as long as your calculation for potential energy will be with respect to that certain datum. Okay, you cannot have a datum here and then change the datum here for another spot. No, you cannot do that. Okay, so next, that's where the 20 cosine 60 is from. And then we have at point B, that's 1/2 800 times VB squared, because again, kinetic energy T is equal to 1/2 mv squared, right? Okay, and here we have 20 cosine 15, because yet again we have another right triangle at this point. Okay, let's see, at this point, and once again, this is the adjacent side, this is 15 degrees. Okay, and this will remain 20, so this equation holds true. All right, so plugging all that in to the conservation of energy equation, then you will be able to solve that VB, or the velocity at which the airplane strikes the ground at point B, is equal to 13.52 meters per second. Okay, now next, since we know the speed, then we have to find the maximum tension, right? Okay, so from this free body diagram, we know that we can solve the maximum tension, right, by applying summation of forces, right? Summation of forces in the n direction. Okay, and equating that to 0, since this is supposed to be in no, not equating that to 0, rather equating that to m a n. Okay, so what are the forces acting on the along the n direction? It is this force right here. Okay, so this is the weight times cosine theta. Okay, and then t, so this will be t minus weight cosine theta, all right, is equal to m a n. Okay, where we know that an is v squared over rho. All right, so we know this from the previous modules. Okay, and this is what we see here. All right, so that's t minus 800 times 9.81 times cosine 15 is equal to 8,000. That's not 800, that's 8,000. 8,000 times 13.52 squared over 20. Okay, and you will find that t is equal to 149 kilonewtons.